start the step 2. Replace symbols with numbers. Again, the point of today's lecture is to use low-level representations of interpreters. Low-level. So step 1 was to replace continuation, which is functions, to records. It was used to be lambda expressions, and now we are using traits. Instead of making lambdas like LV, like that, we made a trait, a class called add, second, K, like that. So high-level functions are now replaced with data. Step 2, replace symbols with numbers, meaning that replace names with numbers. What do we mean by names in machine level? In machine level, everything is zeros and ones. So translate function converts an expression to M expression, machine expression. So there could be many differences, but in this course, because it's so simple and we'd like to just see how that works in a nutshell, so we are going to just change identifiers. Okay, so identifiers from strings to values, and because of that, we are gonna have some others as well, but let's see. The trait expression is now called M expression, and ID is now MID. The others are more like just change the name to prefixed by M. That's it. So identifier in expression, it used to have string name, but now in machine expression, MID has an integer. So previously in expression, when we know a name, that was its identity, that was its name. And now with this M expression, machine ID is not by name string, but by its position. Position, what's that? Position in the environment. So previously with expression, we used environment, which maps names to values. Remember, environment sigma was what? Mapping names to values. String names to values. But this time with this translation environment does not have that. It's just a list of names. Pre-compute substitution positions, meaning that in this translated version, names are positions in the environment. One more time, translate takes an expression with an environment and produces an M expression. Translation from one language to another language. It's like a compilation, right? Very simplified version of compilation. From one source level to another target level. Expression to machine expression. How do you do that? The other things are just recursively calling this translate function, but the base case is that ID, name, is going to translate that to machine ID with this number. What is the number? The position of this name in the environment. The position of this name in this translation environment. We are going to have that function, locate function, in the next slide. Locate function takes a name and a translation environment and returns the position of this name in the environment. What's the position? What's the position of the name in the environment? You know when the names are added to the environment? In other words, do you remember when the names are introduced? Where was that? As a function parameter, right? Either as a function parameter or this name introduction expression, val expression, and we got rid of that val expression because we can rewrite that to function expressions and function calls. So in this simplified language FAE, there's only one name introduction position function parameter. So in this function expression, right, when we have a parameter and a body expression, we are going to have what? Something different. We are going to have only body expression. And fun now takes only body expression, which translates the function body under which environment? The given environment prepended by its parameter. Do you see that? One more time. Previously in this expression, function expression has two fields, parameter name and body expression. In the translated motion function expression, it does not have a parameter because parameters are gone. There are no names, only numbers. And the body expression is now translated, but unlike the other sub-expressions, this body expression is translated with a new environment, new translation environment, which was prepended by its parameter. Meaning that in this function body, when you look up the name, right? When you look up the name, the very first thing is going to be its parameter. Do you see that? Yeah, that's going to be its parameter. So locate function, that's a function that returns the location of the parameter, right? Or the name. Locate function takes the name and a translation environment. When the translation environment is empty, it's an error. Oh no, this name does not appear in this translation environment, which is a list of names. So it must be a free identifier error. Otherwise, this translation environment is a list of names. So, hey, this given name, are you the first one in this translation environment? Are you the parameter of this function expression? Oh yeah, then your number is 0. Oh no, I'm not the parameter of this function body. Then recursively call this locate function with the given name with the remaining translation environment and get the result and add 1 to it. Do you see that? Right? Do you see it? You should be able to understand how the numbering goes on so that when we have lambda x dot lambda y dot lambda z dot x plus y plus z, then how would you translate that x bar to mx bar? Do that by yourself, right? Write down, finish the definition of this translate function, and then call that with this expression with the empty list. Then you should be able to translate this expression to motion expression and see how those x, y, and z are numbered in the function body. Are you with me? Yeah, you should do that by yourself. Otherwise, you cannot understand this thing. Use simple list for substitutions at runtime. And now that we translated, we compiled x bar to motion x bar, when we interpret the code, we are not gonna interpret x bar, but motion x bar. That's the point of compilation, right? That's the point of translation. We'd like to interpret mx bar instead of x bar because it's more low level. It's more machine friendly. So interpreter now takes a motion expression instead of high level expression for people, motion expression and an environment and a continuation. So this environment does not need to be that old environment that maps names to values because we do not have names anymore. Then what is going to be this environment? A list of values. Oh, really? Then how do you know the values of that specific identifier. Now that identifiers are not by names but by position, we are going to get the values of that identifier by its position. So when we interpret an identifier, instead of looking up the environment using its name, we are going to get the value of this position from the environment. Environment that apply position, meaning this, because this environment is a list of values, get the value of that position. Really? Then how do we put that corresponding value into the environment? Remember? Again, names are introduced by function expressions. When do we bind values to those names? You think? When was that? Function call. So continue. When we do actually apply function call, we are going to have closure V and the continuation to do. This time, closure V does not have a parameter name. You see, right? Because names are gone. And this mx per body and the environment. And when we interpret this body expression, yeah, and the work to do is going to be the same. There's no news here. What's going to be the environment when you interpret this body expression? Yeah, this environment is a list of values, not the map from names to values. What is it going to be? We are going to prepend the argument value to the top of the environment. Remember, when we compile that, we put the parameter on the top of the translation environment. Now that we are going to call the function and pass the argument, we need to put that on the top of the environment. If you compile that and add it to the top and call it, when you add it to the bottom, you are gonna be host. 이름을 컴파일 할 때 앞에다 environment 앞에다 붙였으면 함수 콜할 때 value도 앞에다 붙여야 돼요. Because you kept that ordering, you are going to have that. One more time, you'd better do by yourself lambda x dot lambda y dot lambda z dot x plus y plus z, and then apply that with 1, 2, 3. Okay? And see how you can compile this version to mxper, and then how to interpret that using this version. Then you are going to see how those numbering works. So far so good? Okay, then before the second break, let's do step 3. Okay, let's see. Step 3, replace function calls to go-tos. Ooh. There is a really famous paper called Go-to Considers Harmful. Yeah, Go-to Considers Harmful. Go-to는 정말 나쁜 애예요 라는 논문이 있어요. Yeah, go-tos are really bad because that's like spaghetti. Flows go here and there everywhere. It's really difficult for people to reason about and understand. But we are doing low-level representation for machine. So computers do not care. So when we write programs, we'd better use high-level functions and calls and names because we are people. But compilers can nail that down to low-level data structure and go-tos for computers for performance reason. So aside from building records and using primitives like plus, all function calls in the interpreter implementation that we have done so far are in tail position. Do you see? Let's see. In the inter function, for a given machine expression, an environment and continuation, depending on the expression, when we have numbers, identifiers, and function expression, we create num-v, look up the environment, get the value, and make closure v, and then continue, call k. So the last thing for these cases in this function body are calling the continue function. For the other cases like addition, subtraction, and function call that have two sub-expressions, what we are supposed to do is to call this inter function with the first sub-expression in the given environment, and you constructed continuation. Again, the body calls this inter function. Either call this continue function or this inter function recursively. They are all calling functions at the tail position. How about the continue function? Let's see. For a given value and a continuation, call k with this value. Then what is the k? If it's empty k, congratulations, you're done. Return the result. If it's add second k, that means that you were in addition and you interpreted the first sub-expression. What you are supposed to do now is to interpret the second sub-expression using this environment, make a continuation. When you're sub second k, same thing. You are supposed to interpret the second sub-expression using this environment, make some k. When you are at arg k, you are supposed to interpret the second sub-expression, argument expression under this environment and make special k. They are do add k, do sub k, and do add k. Anyway, the body calls functions interp, or continue. They all call functions. Tail position. See? So we are going to change each to mutating registers and zero argument call, meaning that because we do not need to pass arguments. Right? We do not need to pass expressions, environment, and continuation, and with continuation on all that, we are going to have global variables. Yeah, global variables. Who cares? We use gotos. Low level. Not for people. So we are going to have expression register, continuation register, value register, environment register. In this expression register, we're going to have machine expression initialized to 0, whatever. It's a garbage initial value. Top level continuation is not garbage. It's the empty k. Value register, we don't have a value yet, so it's just initialized with some random value. Environment is not random. That's going to be empty environment. So how do we do that? For a number case, we continue this k using this value. What are we supposed to do? Before calling this continue function, which does not have any argument, we set up the continuation register and value register. When we call this inter function, we already have this continuation register. So we are going to reuse the continuation and just change the value register. So put this non-vn to value register, call continue. Okay, it's not yet enough, right? I'm gonna show you more thing like that. When we have identifier, we are gonna use the same continuation again, but we are gonna have different value. So for this identifier, we are going to put that value to value register and continue. For interpretation, okay, we're gonna call interpretation again without any argument. This time, expression is gonna be not addition but the first sub-expression, right? But environment remains the same, so we do not need to change the environment register. Continuation is not k, this new thingy. So again, before calling this inter function, we are going to store L to this export register. We are going to construct this new continuation using what? The second sub-expression all and environment in the environment register and continuation k in the continuation register. Construct this continuation and put that into the continuation register. Just like that. What about function call? Again, yeah, we are gonna change the expression. We do not change the environment. We change the continuation with this new continuation and call inter. Ooh. When we have empty k, return value. When we empty k, we are done, return the value in the value register. Okay, so far so good. When we have add the second k, one more time, we change the expression, we didn't change the environment, and then we call k. We change the expression, we change the continuation. Oh, we do not need to change the environment, right? Let me check. Yeah, we do not need to change the environment. Wait. Ooh, sorry about that. Because we have this environment is not given, we need to push that here. So we need to keep this environment to environment register. So again, the second sub-expression, the environment to valid, and then this newly constructed continuation and call inter. Okay, what about this? When we call continue, we need to have this new k, we need to have a new k with this new value, like that. So that was step 3, and there could be more steps like step 4, replace data types with cons, meaning we constructed this cons and all that with continue and all that, and we can get rid of that and make that as lists. Lists is what? Either empty or a value and a list, which is a pair, right? And step 5, we can replace even lists, which is a pair, with memory allocation. And when we just allocate memory without any deallocation, there's going to be memory leak. So we can add deallocation. And when we have memory allocation and deallocation, because programmers make mistakes a lot, often, right? So that may not be a good idea. There are 2 approaches like C, C++, and those languages, or Java, Scala, and other languages. The main difference is their memory management. C and C++ and those programming languages that allow programmers to allocate and deallocate memories, they give power to the programmers, but when there are issues, memory errors, that's all the programmer's responsibility. And with Java and Scala, garbage collection does the job, so it guarantees that there are not going to be this problem and all that, and that's really easy for programmers to use memory, but it could be slow. So if you want to have reliable, robust program, you may want to have this memory management by language. If you want to fast and efficient program, you may want to use C, but you'd better understand what you are doing. You should take your own risk allocating and deallocating memory. The notorious problem with C and C++ is what? If you do not deallocate, then you are gonna have memory leak, right? If you deallocate too soon, you're gonna have what? Dangling pointer, right? Segmentation fault, seg fault, blue screen. They are all because of the memory management by C. Now let's take the second break and come back for the last part of this lecture.